Hello and welcome to ATI 4640. In this lecture, we will continue addressing forecasting methods and approaches based on the different scenarios. We addressed the naive approach, the moving average, the weighted moving average, and the exponential smoothing approach. Then addressed some of the error measures in the forecasting methods. This session will address time series approaches with some adjustments. Uh, then um, we will look at some examples. Exponential smoothing is a popular modeling approach in business. When a trend is present, exponential smoothing must be modified because of the lag in prediction. Taking trends into consideration, the formula will be forecast including trend, which is FITT, equal um, to exponentially smoothed forecast, which is the FT, plus the trend, the TT, which is the exponentially smooth trend. So f of t will equal to alpha multiplied by the a t minus 1 plus 1 minus alpha multiplied by f of t minus 1 plus t of t minus 1. And the trend can be calculated by another factor, which is beta, multiplied by f of t minus f of t minus 1 plus 1 minus beta multiplied by t of t minus 1, where f of t is the exponentially smooth forecast average, the t of t is the exponentially smooth trend, the a of t is the actual demand, alpha is the smoothing factor or constant for average, which is between 0 and 1, and the beta is the smoothing constant for the trend, which is also between 0 and 1. To compute a trend adjusted forecast, we need to follow these steps. First, we need to compute f of t. Then we need to compute t of t. And the third step is to calculate the forecast f of it of t, which is equal to f of t plus t of t. A large manufacturer wants to forecast demand for a piece of pollution control equipment. Um, the table in this slide shows the review of past sales indicates um, or indicating that an increasing trend is present. So this in this example, you can see the manufacturer data and you can see the trend that we have. The smoothing constant are assigned the values of alpha equal to 0.2 and beta equal to 0.4. So all this are the giving information for the actual demand for the past 10 months for this manufacturing facility. The firm assumes the initial forecast average for month 1 F1 was 11 units, and the trend over the period T1 was 2 units. Using the equation for the trend adjusted exponential smoothing and using the provided values, we can forecast the average for month 2. So first let's find the forecast average forecast for month 2. F of 2 will equal to 0.2, which is alpha multiplied by 12 plus 1 minus alpha, which is 1 minus 0.2 multiplied by 11 plus 2, which is the trend for the first month. 2 is the trend for the first month. Calculating the values and finding the result will equal to 12.8 units. 12.8 units. While the smoothing trend can be calculated using the equation for the trend. So T2 will equal to beta. The beta is zero point 0.4 multiplied by the f of 2 minus f of 1. F of 2 we just found that, so it will be 12.8 minus 11 multiplied by or plus 1 minus zero point 0.4, which is a beta, multiplied by the trend 2. Finding the values will be 1.92 units. So the trend for the second month is 1.92. Now we calculate the forecast including the trend FIT uh, for the second month, which will equal to f of 2 plus t of 2. That's 12.8 plus 1.92, and that will equal to 14.72 units. So the forecast including the trend will equal to 14.72 units. Calculating the forecast average, the trend and the forecast with trend for the rest of the months. The forecast for the 10th month will be 32.48. The trend will be 2.68, and the forecast including trend will be 35.16. Drawing the graph for the results, we can see the actual demand compared to the forecast, including trend. The green line is passing through the middle and very close to the actual demand. So you can see how the green line that we just created, which is FIT, the forecast including trend, is very close, and it passes through all the points on the actual demand. So it's closer to the actual. The last time series forecasting method that will be addressed is the trend projection. This technique fits a trend line to historical data points and then projects the slope of the line into the future medium to long range forecast. Several mathematical trend equations can be developed, but this course will be addressing the linear trend only, or linear trends. Linear trends can be found using the least square technique, where we have y hat equal to a plus bx, the regular symbol equation, where the y hat is the computed value of the variable to be predicted, or dependent. We call it dependent variable because it depends on the x as independent variable. So x is the independent variable, b is the slope of the regression line, and y is the y axis intercept. The least squares method minimizes the sum of the squared errors or deviations from the actual observation and use the formula to create the trend line as shown in the graph. The regression equation, which is y hat equal to a plus bx, b can be calculated through dividing the summation of x multiplied by y minus n multiplied by x bar, or average, and y bar average, or the average by the summation of x squared minus n multiplied by x bar squared, while the y-intercept a will equal to y bar minus bx bar. The demand for electrical power, and this is an example, the demand of the electric power at NY Edison over the past 7 years is shown in this slide. So we have the demand here. The firm wants to forecast next year's demand by fitting a straight line trend to these data. If X is the year, y is the electrical power demand, then the summation of x is 28, y average or y bar or x bar is equal to 28 divided by 7, and that is 4. The summation of the y values is 692. The average of y is 692 divided by 7, which is equal to 98.86. Then we use the formula for A and B to find the values of the A and B. B will equal to 3063 minus 7 multiplied by 4 multiplied by 98.86, all divided by 140 minus 7 multiplied by 4 squared. And that is 295 divided by 28, which equals 10.54, while A will equal 98.86 minus 10.54, that's the B value that we just found, multiplied by 4, which equals to 56.70. Thus, y hat will equal to, the formula will be 56.70 plus 10.54 multiplied by x, and this is our formula for y. And again, y is dependent on x, so whatever the value of x will decide or will determine the value of y. So if the demand in year 8 or y8 will equal 56.70 plus 10.54 times 8. So when we say year 8, the demand in year 8, so y is the demand, y8 is the demand for year 8, will equal the value of 141.02, or we can round it down to the nearest, which is 141 megawatts. That will be the power demand for that month. So again, what we did, we found the value of A and B. We replaced those values in the formula of Y. That formula will assist us in finding the values of the demand over the years. So when we change X, which is the year, year 8, year 9, year 10, so on, that will give us the new forecast for Y, the demand. The graph shows the trend line according to the equation, which provides the least deviation from the actual. To apply the least square method, we have to plot the data. Ensures a linear relationship. We don't predict time periods far beyond the database, and deviation around the least square or least squares line are assumed to be random. The multiplicative seasonal model can modify trend data to accommodate seasonal variation in demand. If you remember, we said that when we have seasonal, it will be different. So with that, so we can add the seasonal model to modify the trend data based on that. For example, the jet ski and the snowmobile that we addressed in a previous session. So to do that, we need first to find the average historical demand for each session or for each season, then compute the average demand for all seasons. A calculated seasonal index for each season can be created by and used to estimate next year's total demand. So dividing this estimate of total demand by the number of seasons, then multiplying it by the seasonal index for that season will give us the estimate of the certain month of a certain month in the next season. For example, a distributor of laptop computers wants to develop monthly indices for sales data from the past 3 years by months are available, and you can see year 1, year 2, year 3, and we have from January all the way to December all the data available for us. So we first find the average historical demand for each month, uh, and that will be by adding the 3 years at that month, January, for each year, and then divided by 3, we'll get the 90. Then we do the summation for these averages, and the summation came out to be with us as 1128. The average monthly demand will equal the sum of the average period demand divided by n, the number of periods, which is in our case here will equal to 1128 divided by 12 months. Those are the periods, and that will equal to 94. So to find an average, and we just the same average for all months, we divide the 1128 by 12, and we will get 94 for all months. To compute the seasonal index, we divide the average monthly demand for the past 3 years by average monthly demand, which is 90 divided by 94. So basically, we divide the average period demand by the average monthly demand, 90 by 94, and that will give me the seasonal index for that month. Using the formula, we compute the seasonal index values as shown in the last column for all the months, as you can see here. So this is our indices for all months. We can, using the computed value, the computed index values, we can use it to forecast the monthly demand for the fourth year for each month. So for example, if the expected annual demand for computers for next year is 1200, what will be the monthly forecast demand using the index? Again, with the 1200 instead of 1128, with 1200 we divide by 12, and then we multiply by the indices or index for that month. For the first month of January, 1200 divided by 12, and we multiply by 0.957, and that's the adjustment for that month, and that will equal to 96 for January. Then we multiply by the adjustment for February, and we'll get 85, multiplied by the adjustment for March, get 90, and so on, until we get all the values for all months. And this is the forecasted demand for year 4. So we have all the information from year 1, year 2, year 3. We use that to create indices, and the indices assisted me to find the demand for each month in the fourth year. Drawing the graph of the forecasted demand for different years based on the seasonal index, we can determine the trend over the years and where it's going, as you can see. Another example is the San Diego hospital that wants to improve its forecasting by applying both trend seasonal indices to 66 months of data it has collected. It will then forecast patient days over the coming year. A trend line is created, then monthly seasonal indices are computed. Then the model will be used to forecast months 67 to 78, the next 12 months. Using the historical data to calculate both values of B and A, the formula will be y hat equal to 8.090 plus 21.5x, where y hat is the patient days and x is the time in months. Based on this formula, for the next month, period 67, patient days will equal to 8090 plus 21.5 multiplied by 67. Um, uh, I'm sorry, I said 8.090. Actually, it's 8090, not 8.090 in the previous I had. So I read that by mistake. So the patient days, which will equal to 8,090 plus 21.5 multiplied by 67, and that will equal to 9,530. Completing the calculations for the rest of the month, we will result the trend line shown here, and you can see that we have the 9,530, 9,551, 9,573, 9,594, 9,616, and so on. Then we use the data to calculate the seasonal indices based on the 66 months data. And those are the index as we did with the previous example. With the data existing 66 points or 66 data points, we can use it to calculate the average, and then we use it to calculate the indices or index for those months. The seasonal indices line is shown in this graph. Neither the trend data or the seasonal data alone can provide a reasonable forecast for the hospital. Only when the hospital multiplied the trend adjusted data by the appropriate seasonal index did it obtain good forecast. So patients days will equal to 9,530 multiplied by 1.04, and this is the index that we got for that month, and based on that we will have for the month of January 9,911, and this is with adjustment, the trend with seasonality. So the forecast with trend and seasonality will be calculated, and as you can see in this table, it's shown for the other months from January all the way to December, and that will show or adjust that. So by combining the trend and the seasonal forecast, the hospital was better able to forecast patient days, which also assisted in staffing and budgeting for the next 12 months. Cycles are patterns in the data that occur every several years, and forecasting cyclical variation in a time series is difficult because cycles include a wide variety of factors that cause the economy to go from recession to expansion to recession over a period of years, maybe 5-10 years or more. So a linear regression will be when you have more factors, you can use a linear regression where you have more than one x, so you will have at that point x1, x2, x3 factors we consider as independent variables that can affect y as dependent variable, the demand, and the forecast will be based on these factors. So that's with a regression model. But with our course here, we're not going to go through the regression model and the complication of the regression model. So that will be all for this session. If you have any questions, please let me know. Thank you and have a great day.